everybody, welcome to our third and final oceans lesson. Today we're looking at food chains, but you can watch them in any order. Worms get eaten by birds and birds get eaten by cats. That's a food chain. It's not rocket science. It's a lot more complicated than rocket science, honestly. I gave you some organisms, that just means like plants or animals, and said what's the longest food chain you could make with those organisms. Phytoplankton gets eaten by krill, which gets eaten by squid, which gets eaten by crab-eater seals, which gets eaten by leopard seals, and they are even sometimes eaten by killer whales. If we're going to learn about food chains, you need a lot of keywords, okay? So I'm just going to tell you some keywords. At the bottom of a food chain is always what we call the producer. By far the main producer in the sea is phytoplankton. It's very, very small organisms, and phyto means plant, plankton means made to drift, so they're like the little drifters of the sea. It actually could be bacteria or it could be a plant. It's just anything that can capture the sun's energy and use like carbon from the atmosphere and nutrients in the sea to make food. So they provide pretty much, I'll tell you at the end some creatures that can survive without this stuff. But they make food for pretty much everything else in the ocean, and they also help us because more than half the oxygen we breathe comes from phytoplankton in the sea. How crazy is that? So they're the producers, and then everything that isn't a producer is a consumer. So you've got primary consumers, or you could call them herbivores because they only eat plants, which in this case is the krill, but it could be like zooplankton, which are sort of like phytoplankton, but they're tiny little animals like baby creatures and that also float along. Or even green turtles, or fish, that kind of thing. This squid would be a secondary consumer. And then right at the top, you've got the top predators. So a predator is something that hunts and kills another creature. So killer whale in this food chain is the top predator because it isn't eaten by anything. It only consumes the things below it. Other top predators, tuna, very big sharks, leopard seals are usually thought of as a top predator, although apparently killer whales do sometimes kill them. Marlin, if you ever read the fantastic book The Old Man and the Sea, the fish that he was captured, that's top predator. They tend to be fast, very good at catching prey, live quite a long time. We're going to look at some of the mad skills that they use. Our activities today are based around what they do. Cool fact that I learned while researching this. So you can get carnivores, which eat meat, herbivores, which eat plants, and you can also get omnivores, which eat both. The bonnet-head shark, which looks nothing like this, is an omnivore. Yeah, 65% of its diet is seagrass. How sweet is that? So sharks, really bad reputation. Some of them just eat a lot of grass. Isn't that nice? Question that I would ask my kids at school, what is wrong with this food chain? So I've got a couple here. Killer whales eat squid as well, so you could make a food chain like that. Or leopard seals even eat krill. So these are a couple of food chains that you could have also made. What is the issue with food chains? What is sort of coming to light here is that they're far too simple. They do not tell us the full story. You want one of these, really. This is a food web. It's a much more accurate depiction of what's going on, but as you can see, it is also a lot more complicated. So the arrow direction is a bit confusing, isn't it? People always think that the arrow should be saying eats, but phytoplankton doesn't eat krill, and krill doesn't eat leopard seals. This is showing you where the energy is going. So the energy starts here because the phytoplankton captures the energy from the sun, and then unbelievably, it's that energy which is then passed on to the krill in the form of the sugars in the phytoplankton, and then that krill passes on some energy to the leopard seal, and the leopard seal passes its energy to the killer whale. So that's why the arrow is pointing that direction. If you want to say like gets eaten by, that makes it easier to remember. So yeah, as you can see, food webs, pretty complicated, aren't they? I'm going to show you for the first time ever an image that I do not have the rights to, because it's just being passed on from teacher to teacher to teacher on like the teacher internet. I think it must be from a really old textbook, but look at that. How gorgeous is that? It's an ocean food web, which obviously we're not going to go into in a lot of detail, but isn't that beautiful? Someone's taken the time to do that. That just gives you an idea of how incredibly complicated the ocean is. So what this tells us is that animals have a lot of different ways to eat and a lot of different ways to be eaten. So one of the things we're going to look at today It's how animals avoid getting eaten, and also how they've learned to be very good at attacking things. So you get two different kinds of predator. You get pursuit predators, which do what it sounds like just chase things very fast. We're going to look at a minute how squids move really quickly. And you also get ambush predators, which hide and attack. So the leopard seal in our picture, it can even catch penguins because it just hides under ice. And then when a penguin dives into the ocean, have you ever seen Happy Feet? Actually, quite scientifically accurate in that sense, because I think the seal is weighted and then like jumps on it. Yeah, crab eater seals, they've adapted to have teeth which can filter, so they sort of take in water and the water leaves, but the krill stay in their mouths, so they eat a lot of krill. But yeah, let's have a look at what squid do. So squid have got to be able to move really, really fast in order to catch things and in order to run away, because they're in the middle of the food chain. So I'm quite pleased I found 2 uses for a squishy plastic bottle in this lesson. What we're going to do for the squid is literally just put the plastic bottle into your washing up liquid bowl full of water and give it a squeeze and see what happens. Don't deform it because we're going to need it later. Squid have got this like cloak of soft tissue around their bodies, which is called the mantle. So if you imagine that the squid's body is inside our plastic bottle, they fill the mantle with water, which is what I'm doing now, which takes quite a long time, by the way. So this is like not a flawless technique, because obviously if you're quickly trying to fill your mantle with water so you can get away and something's catching up to you, then that, it's not ideal. But they fill the mantle with water, and then what they do is they shoot the water out of a tube under their heads called the siphon, and like that. And if you do that, then you should feel the bottle is moving away from you in the opposite direction. Do you know why that is? It's because everything is really physics. Isaac Newton, we talk about him a lot, said that for every action there is an equal and opposite reaction. The bottle is pushing on the water and the water is pushing on the bottle. So the water's moving in that direction, but if the water's pushing away in that direction, that means the bottle is pushing in this direction, and that is how the squid moves around. Now, I only learned this last night, so I haven't actually had time to do it. But I also found out that the aperture of the siphon, like on a camera, just the sort of size of the hole, squid can change it, and that makes them go like faster or slower. So I've only got one hand here, but try with one hand, maybe covering up the siphon with some fingers to make it smaller, and then push again with the other hand, and see if you can feel the difference, and then let me know. Okay. Now, when you finish that, actually, you can keep the water in the bottle. See, it's all about reusing, because we're going to use that later. And we're going to use the water which is in here now as well, because, again, physics. The speed of sound in air is about 343 metres per second. So sound travels fast in air. Sound in water travels a lot faster than that. 1,480 metres in 1 second. Whales take advantage of the fact that sound travels really well through water to slap their tails onto the water, scare the fish, move them to where they want them to be. Just tap the side of your washing up bowl and see how clearly you can hear the sound. Pretty clearly, because that sound is travelling through the air to your ear at 343 metres per second. Won't be good telly, will it, unless I actually show you what I'm doing. So put your ear in the water and then tap it again. Oh, it's so cold. Take it out, put it in. You should hear that. You hear it a lot more easily. Didn't really think about the consequences of dipping my ear in water halfway through the lesson, but again, you can try that in the bath. I think I'm going to have a break next week, but I think the week after we will actually do sound, so we can look into that in a bit more detail, because whales use sounds in an absolutely incredible way. Standard school question then, okay, here's your food chain. What would happen to leopard seals if human beings hunted all the killer whales? Okay, if there were no more killer whales, then what would happen to the leopard seals? That's like a classic little exam question for you there. If there weren't any killer whales, then there wouldn't be anything to eat the leopard seals. So there would probably be more leopard seals in the sea. You'd get more of them, okay? What would happen to the krill if suddenly we took all the squid out of the sea? What would happen to the krill if suddenly we took all the squid out of the sea? Well, if we took all the squid out of the sea, you would think that there would be loads and loads and loads more krill, wouldn't you? But actually, we have found out here that leopard seals eat krill as well. So maybe if we took all the squid out of the sea, then there'd be loads and loads more krill. But then maybe because there was loads more krill, you might get loads more leopard seals. And then because there were loads more leopard seals, you might get loads more killer whales. So this is why I say that food chains are actually much more complicated than rocket science. And to prove this to you, I have a real life example. A lot of whales, they only eat krill. We thought that one of the consequences of whale hunting would be that the krill population would explode because there's nothing eating them. In fact, that did not happen. And this is a thing that scientists call the Krill Paradox, because it didn't seem to make sense. Why, if you're killing the things that are eating them, do you not get loads more krill? And it turned out they think the answer is that the whale poo was fertilising the phytoplankton, so making it that there was lots of phytoplankton, and the krill eat the phytoplankton. So actually, even though the whales were eating the krill were dependent on the whales because the whales were producing their food. So our story time today, which we're actually going to go to now, is all about how food chains are a lot more complicated than you might first think, and you shouldn't mess with them. Just past the Grand Canyon in America, there is a beautiful expanse of land called the Kaibab Plateau. And in 1905, 4,000 deer regularly grazed the Kaibab Plateau. It was a beautiful sight. People came from all over the country to see these beautiful deer. And eventually, Teddy Roosevelt, the president of the United States at the time, said, guys, we have to protect this place. This is a beautiful place. I'm going to make it a national park, and then the deer will be safe forever. And everyone said, oh, that's a brilliant idea, okay. What do? Okay, you're Teddy Roosevelt, you want to protect all these deer, make sure that they stick around so that everyone can enjoy them. What do? He did two things. The first thing that he did is to say no one is allowed to hunt the deer anymore. We will have no more hunting of deer. No. And the other thing he did, slightly more controversial, he allowed people to hunt the predators of the deer. So between 1907 and 1939, 816 mountain lions were killed, 7,388 coyotes were killed, 20 wolves were killed. Oh, sorry, I don't have a toy wolf. And over 500 bobcats were killed as well. So what do you think happened then, right? There's no predators to hurt these deer. No one's hunting the deer. The deer population exploded. Loads and loads and loads of deer because there was no one and nothing to keep them under control. So we've got loads of deer now on the Kaibab Plateau. People weren't keeping a particularly good tally at the time, but they reckon certainly upwards of 10,000 deer. I remember we started out with 4,000. So what happened after that? What do you think would happen now? There's loads and loads of deer, loads more than there used to be on the Kaibab Plateau. Well, what happened is they ate all the grass. The grass got more and more and more depleted. And of course, lots and lots more deer means lots and lots more deer trampling all over the grass as well. So eventually, there is basically zero grass on the Kaibab Plateau. So suddenly you got no grass. What happens to the deer? Well, yeah, that's right. A lot of them died. They estimate that 60,000 deer starved in 2 winters on the Kaibab Plateau. Now, eventually, the government said, oh, please, everyone, stop hunting the predators, and they introduced more predators, and they started hunting the deer again, and eventually the deer population did stabilise, but it stabilised at a much, much lower number than there had been before they tried to protect the deer. So the lesson that I used to teach my children is don't mess with food chains. Now, it's got a surprise ending because I found out some new information while I was researching this story. In 1970, a scientist called Graham Cowley reviewed all the evidence of this case, because what happened is this story was seen as a textbook example of how you shouldn't mess with food chains. So textbook after textbook after textbook had published this story, and finally Graham Cowley came along and realised that actually the textbooks are wrong, and that the predators, he said, had had very little to do with the depletion of the deer population, and it was actually probably caused by changes in climate, livestock grazing, and changes in wildlife policies. So Graham Cowley, what you're telling me is that the actual lesson of this story is that food chains are even more complicated than a science teacher thought, and I'm not allowed to tell this story anymore. That's the story we got about plateau, because it's still a great story, and it still kind of shows us that you shouldn't mess with food chains, until blooming Graham Cowley came along. I've saved the best activity till the end, because I think some of you might take a bit of time to get it working, and it means that I can say goodbye, and then you can keep playing. Okay, so what we're going to do now is we're going to have a look at fish bladders. So what you need to do is fill your plastic bottle with water. We're going to look at the difference between fish and sharks, because fish and sharks are both denser than water. The shark and fish is, like, generally speaking, heavier than the amount of water that space would fill. So fish and sharks technically should sink, but why don't they sink? Well, fish have something called a swim bladder, which we're going to recreate with our experiment. Sharks do not have swim bladders. If I pour this oil into this water, what is going to happen? Okay, if I pour some oil onto some water, what happens? Come on, you've been doing loads of science activities, haven't you, during lockdown? You know this. Make a prediction, please. There you go. It floats, doesn't it? Oil floats on water. And that's because oil is less dense than water. So what sharks do to stay afloat is they have really big livers full of oil, and that helps them keep afloat. The other cool fact about sharks is they don't have bone. Sharks do not have any bones. They have something called cartilage instead, which is what your nose is made of. That's why if you look at a human skull, there's just a hole where the nose would be, when obviously it sort of feels like there's bone there, doesn't it? But it's cartilage, because that's a lot lighter than bone. So that's what sharks do. Fish have a swim bladder, which we are going to try and recreate now. You need the lid of a biro that looks like that, a squishy bottle full of water, and you need a lid for that squishy bottle as well, and some blue tack. My biro lid has got a hole in, so I'm going to cover it up, because you don't want a hole in the top of your biro. There we go. And I'm going to put in, you just need enough blue tack on the bottom of the biro so that it just floats in the water. Caitlin, you thought it was ears. Yeah, I was quite pleased with that cool shark quiz question. Do sharks not have ears or tongues? It turns out, yeah, they do have tongues, although actually they don't taste like us. Their taste buds are on the sides of their mouth. So it's kind of a trick question. Right, let's see if I can get that floating. Oh yeah, that's pretty good, see? So you want something like that. Right, so I've put the lid on that, and hopefully, like I said, I've done this at the end, so if it doesn't work for you, you can keep fiddling when I've gone. When you squeeze the bottle, you should see something cool. Oh, look at that! And then unsqueeze. What? It's just, it never stops being exciting. Squeeze again. Hey, and go up again. What is happening there? Well, that is exactly how fish, it's very similar to how fish move around in the water. You have trapped an air bubble inside your pen lid. And when you squeeze, water can't really be compressed. Like we've discussed, water particles are quite close together. But air particles are really quite spread out, and they're very happy to be compressed. So when you squeeze, the only thing in the bottle that is being compressed is that air. Now, because the air is compressed, it takes up less space, so a little bit more water moves upwards, and that means that the lid is no longer less dense than the water. If you want to know a bit more about density, I did a hot air balloon lesson where I've got diagrams going into a bit more detail. But for now, we'll just say that because the contents of the pen lid are denser than the water, then it sinks. And then when you stop squeezing, all the air particles spread out again and the contents of the pen lid become less dense than the water. So it floats. I know, right? How good is that? Now, so this is how fish move up or down vertically in the water. Sharks have definitely got one up on the fish, because one of the things that you can do to a fish that you can't do a shark is obviously compress it. So if fish swim too low or too high, then their swim bladder gets too squashed or too spread out and they like explode or get crushed. Whereas sharks, because they've got all sorts of other cool stuff going on, like cartilage instead of bone and liver, they can just use their fins to sort of swim really low down and really high up. They think this is a massive advantage for catching prey, because no one's expecting, if you live deep down in the ocean, fish aren't expecting a shark to suddenly appear from underneath them. We've nearly finished our lesson. I'll let you have a play with that, but I wanted to quickly talk about scavengers, because we haven't mentioned them. We looked in our Ocean Zones lesson at how everything in the ocean, like all the food and the poo, eventually sinks right down to the bottom of the ocean. And scavengers that live on the bottom of the ocean, these are things that don't hunt anything. They eat the dead stuff. But how does all those lovely nutrients get back up to the top of the ocean? Well, it turns out that particularly in North Antarctica, there's a very, very strong wind. And what that wind does is it pushes the surface of the ocean away. And because the surface of the ocean gets pushed away, this creates some space, and all the nutrients at the bottom of the ocean can float up again. So this happens a lot near islands, which is why often around islands you've got all these beautiful coral reefs and stuff, because there's loads of really gorgeous nutrients there. And the other final thing that I want to talk about is how all this ocean stuff relates to finding life on other planets, because quite recently scientists discovered something called hydrothermal vents. Really deep down, absolute bottom, surface of the ocean, very cold, very dark, definitely no sunlight there. But hydrothermal vents are pushing nutrient-rich warm water out of the surface of the Earth. Actually, there are creatures that can use the chemicals from these hydrothermal vents to make their own food. So there's other creatures living off these creatures. So there's a whole food chain right at the bottom of the ocean which doesn't rely on sunlight at all. And this is incredibly exciting if you're an astronomer, because take like Europa, one of Jupiter's moons, we're pretty sure now that Europa underneath its surface has an ocean of salty water. So it's quite possible that there are hydrothermal vents on Europa, and that there is life down there, even though, you know, there's nothing on the surface that we can see. So there you go. Science is all connected, isn't it? We thought we were learning about oceans, and we're actually learning about space. And that ends the final lesson that we've done this week on oceans. I really hope that you enjoyed that. If you haven't liked me on Facebook and followed me on Facebook and subscribed to my YouTube channel, then all that stuff is incredibly appreciated. I'm posting a load of stuff out to my patrons soon and finish their magazine. These are the incredibly generous people who are supporting me monetarily on Patreon. So if you go on my Facebook page, you can find out more details about that. If you want to give me a £5 a month, then you will have access to this magazine that is so close. I'm so proud of it. I can't wait to send it to you guys. Yeah, thanks very much for joining me. See you soon. Bye. Are there any questions? Any birthdays? Did I miss anything out? I didn't get to talk about plastic in the ocean. I figured that we did a whole plastic lesson and it was all getting a bit depressing. But plastic in the ocean is a problem because, like, krill eat little bits of plastic. Leopard seals eat loads of krill, so they eat more plastic. Killer whales eat loads of leopard seals, they get even more plastic. So you end up with a lot of like plastic and pollutants right at the top of the food chain. What's the most dangerous animal in the ocean? Gail, is that a cool joke or like a riddle because it's humans? Or is it an actual, are you actually asking me? Louise, you've watched all my videos. I was thinking, I watched the Royal Society's like big science quiz the other day, and I thought, Louise, maybe for people like you who've seen them all, I should do some sort of big epic quiz of like everything that we've learned over lockdown, see how much we remember about leaves and rainbows and all that stuff. Oh, bye Tom and Charlie. Oh, big fan of Charlie. Yeah, I hope you take take your plastic bottles into the bath, won't you, tonight, and do a bit of squidging. The most dangerous animal is the box jellyfish. Yeah, box jellyfish. I had box jellyfish written down somewhere. I think I had them written down as as a pursuit predator. So you might be right. So I'll go and start editing all those videos so that if you missed anything, you can go on YouTube. Cheerio.